So we've talked about procedural programming. What is it? Some of the strengths and applications, contrasting it against object-oriented programming for the most part, since that's what we're familiar with. Okay, so, and I think we saw some things. We saw a simple hello world. We talked about some of the design goals of Ada. This really comes from a background of really software engineering, trying to build large, reliable systems while maintaining efficiency. And one of their strengths is, so it's phrased here as concern for the programmer, meaning the code is readable and the principle of least surprise. Code, you look at some code and you sort of think what it should do, and that's probably exactly what it does do. And there aren't as many gotchas as you might find in other languages. So we will see that there's one of the biggest things we're going to see and learn about and be exposed to in this class is Ada's type system and how you can really specify the types you want in a much more flexible way than we're used to. So it's very expressive, lets you talk at the level of your problem domain. That's high-level programming. But it also has, if you want to be doing low-level programming, that is your domain is hardware, well then it also lets you express that. So, okay. And just a little minor comment almost, superficial syntax differences. You've seen syntax of Java, which is derived from C and the C family. The algol family just has a different flavor to it. Rather than use curly brackets, you tend to use begin end. You have the open curly brackets corresponds to keywords like loop or is, and a closed curly bracket will end things with end if or end loop or end and then the function name. One thing that's interesting in the C world, they used the equal sign, the thing that you've been trained from K through 12 and beyond to mean, hey, equals is one thing equal to another. And in C, that's assignment. And that just sort of breaks this connection. Whereas Algol and Pascal and Ada have said, hey, let's use some other symbol for assignment, and they use colon equals. So that frees up the fact that now you can check for equality. You can just use the equal sign, just like we expect, principle of least surprise, rather than needing to use equal equals to check for equality. So, and one other thing that we'll see in a moment, in fact, maybe I'll show a program right now. Declaring variables is a little bit different. Let's go look at, what do I call it, assign demo. So here's a short program. We've seen the hello world. Here's a short program. It doesn't do anything interesting. Procedure, assign demo is, and then rather than saying int n, the type followed by the name of the variable, we're going to do it the other way around. We're going to have n colon integer. Okay, so yeah, 6 of one, half dozen of the other, but okay. So here we see n is of type integer, and then we go ahead and begin, and we assign n to 3. Okay. So, and again, like we say, we have procedure assign demo is, then all the stuff, and then includes some declarations followed by begin, the code block, end assign demo. So, okay. So again, that's just a different flavor that we'll be seeing and working with. So again, what are we going to learn in this class? What programming concepts? Programming without classes. We'll see what that means. Which again is like having a lot of static methods in Java. How the language accomplishes some of the things it does. We'll talk about what's going on underneath the hood or what it must be compiling to. We'll see its type system. Okay, and in particular numeric ranges, subtypes. Programming without references. So, and that's going to be a big one. That's the difference between objects versus pointers to objects or references to objects. And you can have both of those in Ada as you can in C, but you can't in Java. So that's going to be new. And with pointers, we'll have explicit memory allocation, deallocation, and dereferencing pointers. So, okay. So let's go ahead and look at some examples. So first of all, we say that there's an expressive type system. Here's one example. There is in addition to integer, there is a type called natural. What are the natural numbers? 0, 1, 2, 3, 4, the counting numbers. And that's an incredibly useful type that I want all the time. All the time I'm making variables in my Java program, and I really want, this is really going to hold a natural number. Int is what I end up using. It's about the only, there is no unsigned int built into Java. And so being able to say natural, and this communicates better to other programmers reading my program, right? They're like, oh, hey, you know, if an index is looping through an array, declaring that to be type natural helps cue you in that, hey, it's never going to be negative, should never be negative. Okay. Here's another interesting thing here. A new variable called small. Its type is colon, and here's the type on the right. Not just integer range 1.10. Okay, so range is a keyword that can be used on ordered types, and you can say it's basically a subrange of the entire integers. Okay, so integer range 1.10, and now if you ever try to assign 11 to that integer, it will signal an error. Okay. It will happen at runtime, okay, perhaps. So for instance here, if n is declared natural and you later try to say, hey, take n and assign whatever value n had, put that into small, well, that might work, it might not. So it won't be a compile error, but it will be checked at runtime. So, in fact, I think we have a, oops, we've got subrange demo here. So here's n is a natural, small, integer range 1 to 10. Here we'll assign n to be 4. Let's start with n as being 3. N is 3, small is n times n. Okay? So we can go ahead and look at this, and you might think, again, the compiler is saying, hey, n is a natural, and square, it's going to be any natural number. Can I assign that into something of type integer range 1.10? Let's go ahead and try it. Let's go ahead and make subrange demo adb, and it compiles just fine. And when we run it, it runs just fine. Let's go back now. I'm going to make one little edit here and just change n to be 4. Okay. So now we're going to go and compile this. Now, of course, detecting that range is a runtime issue. Oh, wait a minute, it's actually, hey, warning, value not in range on line 5. Constraint error will be raised at runtime. And if we go ahead and run subrange demo, sure enough, it raised constraint error on line 8. Range check failed. Wow, that compiler error message was telling the future. Okay. If you think about it, like, whoa, is it running the program when it compiles? This is constraint or constant propagation. So if n was being read from a file, it couldn't have known what n would be, and it couldn't claim there will be an overflow. But in this case, it can prove, it does some work to prove that there will be an overflow, and signals that right at, warns you at compile time. So, okay. As opposed to doing something like this, when we do that, we get a warning. Okay, it's the same thing. Warning, value not in range. Constraint error will be raised at runtime. This time on line 7 instead of line 8. Okay, so yeah, those are things you just can't do in Java, and you never maybe knew that you wanted to do them. After you've seen, especially the type natural or unsigned int, once you have that, it's hard to go back to Java and say, like, oh, I really want to say, be more precise about this type that I'm declaring, but Java won't let me. This is the most I can tell Java about my variable. And I want to say more. I want to say it's just going to be a natural, not any int. Okay. You can go ahead and there is a subtype as well as a range. You can have a new type. So we're declaring a new type here. Negative is a subtype of integer. And it's actually integer range. And this should be integer tick first, which is the smallest integer. Integer goes from negative 2 billion up to positive 2 billion, like in Java. Okay, so yes, and then you go ahead, once you say subtype negative is blah, 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 it's defined as this new type, and you can use it as a type. Okay. Let's go ahead and, actually, we'll go ahead and just try this. Let's clear the screen, start up a Java shell. I'm going to go ahead and, this is now Java, straight up Java. Double penny gets 0.01, double sum gets 0.0, and then the web page has a for loop. Just to save some typing, I'll use a while loop. While sum is less than 1.0, go ahead and sum plus gets penny. Okay. So we know what's going to happen, right? Sum starts at 0.0. It's going to get incremented by 0.01, 0.02, 0.03. Keep on going while it's less than. It's going to get up to 0.99, get incremented to 1, and that's when it's going to stop. So when we finish this loop, sum we know is going to be equal to 1. 0.000007. Okay, well, why is that happening? We're using doubles in Java. Doubles are an approximation to the correct value. They use a fixed number of decimal places. Well, a fixed number of binary places, a fixed number of bits. Doubles use 64 bits. And so just like 1/3 can't be written with a finite number of decimal places, 0.01 can't be written with a finite number of binary places, with a finite number of bits. So it gets truncated. It keeps it to 64 places. That's a lot. But then it stops, and it's not quite right. And when you add it up 100 times, you get some error that actually kind of accrues a little bit. So, okay, well, and in Java, the lesson is, hey, remember that doubles are an approximation to the real number you want, and never compare doubles with equal. Always check if they're close to each other. And actually in Java, you'd say the solution is, hey, we shouldn't be using double to represent money. We should be using int. Let's keep track of our money in cents, not in dollars, not in euros, not in pesos, in cents. And so, yeah, I have 483 cents in the computation. Whenever I print it out, I might divide by 100, and whenever I read stuff in, I might translate it, but internally I'll keep track of everything as an int, where I don't have at least accuracy issues going on with the floating points do. So I can do that. An ada programmer might say that's a bit of a hack, that you're having to go, you want to think in dollars, but you're making your program talk about cents. Okay, so here's what you can do in ada. We're going to find a new type, not subtype, but type dollars. And we're going to take range 0.00 up to 1,000,000.00, so a range of doubles. It realizes what that is, with this delta 0.01. So dollars can take on the value 0.05 or 0.06, but nothing in between. Okay, so now you can go ahead and run this program in ada, and it will go and come out as exactly. When you finish the loop, you'll be exactly 1.00, because you can't be 1.007. You can be either 1.00 or 1.01, but nothing in between. So, okay. Yeah, and again, you can express what you want better. Okay. You can even go ahead, here's a subtype of integer. Subtype even is integer with a dynamic predicate. Even mod 2 is equal to 0. Hey, every even number must maintain this predicate, must always meet that that constraint. This is a pretty simple one, even mod 2, but you can imagine more complicated constraints about being prime, about having some very complicated mathematical definition that we're not even sure about the mathematical properties of overall. So, okay. Anyway, like a type that is one of the zeros of the Riemann zeta function. Yeah, we know a bunch of those values. We can compute if it's a zero or not. Well, we can put that in as a predicate and then have that type in our program. So, okay. You might think about what's going to go on here. If you assign a natural to even, again, like we saw before, it will go ahead and it will compile. But at runtime, if it's the thing you're trying to put into E is not actually even, it will have a problem. E gets E plus 1. You'd think, oh, maybe that should be caught at compile time, because we know we can prove that can never happen. And we'd like it to be caught at compile time, but if you think about it, that actually requires some knowledge of math and the structure of how mod works, mod 2 in particular. So, okay. Yeah, so this may not get caught at compile time, unless you maybe have some sort of proof assistant that you're running at compile time that's looking at your code and trying to prove theorems about things, and it might realize that this is something it cannot ever hold and tag it as an actual error. Okay, so, and Spark is a system for Ada that tries to catch do such proofs at compile time. So, okay. Here's what if I went ahead and just did a subtype even as integer with dynamic predicate even mod 2 equal 9? Well, if you think about it, nothing can meet that predicate. Okay, there is no value at all that will ever make that true. So even is really an empty set. So the moment you try to assign anything to even, it will give an error at runtime. Okay. And again, we might be able to prove that at compile time, but that's a much harder thing to do. So I'll try to be quick here. So I'm going to scan over things, give you a flavor of what Ada will be doing. We're not trying to learn all this. You're not supposed to remember all these keywords right now. We'll cover them again later. I want to talk about a single bit, like a Boolean. Type bit is an integer that is in the range 0 to 1 with size being 1, and this is a size in bits in general. Okay, so you can actually do this, and this will actually make a data type that is 1 bit big in memory, as opposed to, say, a capital B Boolean in Java, which is something like 12 bytes or something like that. It's crazy. Okay. A bit array, okay, type bit array is an array whose indices are 1 to 32. So this actually separately, just arrays. In Java, you say an array has 10 elements. Its indices are 0 through 9. You can't control where they start or where they end. It turns out if you want to start at 1, you're really not happy starting with 0, you can go ahead and say start at 1 to 32. You could even say an array that goes from 10 to 42 if you wanted to, and that's perfectly fine. Okay, so type bit array is an array of this other type with size 32. Okay, so, and actually with the with size clauses, you could go ahead and omit this one and would still be 32 bits long. If you omit this one but keep this one here, could have figured out that bit would have to be size 1, maybe. Anyway. Okay, so you can make our own types like bit array and declare that. So, and now you are, again, kind of close to the machine. In fact, fully getting close to the machine. Here's what will make the C programmers happy, or even jealous, perhaps. Say I go ahead and I have a type sensor. I'm writing a device driver or something like that. Type sensor is a record. Okay, so record is like a class with fields, but we won't have methods, we just have the fields, okay? So a record or a struct or a class. Type sensor is a record with 2 fields, active of type Boolean and temperature of type integer in a certain range, okay? And then you can even add this for sensor size, use 8, okay? And for sensor, use the following record. Active is at 0, starts at 0 and occupies the range 0 to 0. Okay. Actually, I'm not sure about the @0, sorry. But active in that bit field of 8 bits, this will use from 0 up to 0. Temperature will use bits 1 through 7 of those 8 bits. So you can really assign the layout within that. And if you don't, we could have put temperature at 0 to 7 and active at 8 to 8. And that would also work just fine. The order we declare them in here does not need to be the order they end up being laid out in. So, okay. C programmers will have something like this, and in their heads they'll be thinking about what how the compiler is laying them out, and so they'll be thinking in terms of this. But here's the glitch: in C programs, you don't actually always know how it's done, and it can change from operating system to operating system, or rather architecture to architecture. You take the same C program, compile it on a different architecture, the layout might be different. So go to an architecture with 64-bit words rather than 32-bit words. That can really change everything. So, okay, and then we're going to end up here with pre and post conditions. That's our last example of code. So pre and post conditions, and we've talked about these in software engineering and so on, that, hey, you call it a method or a function. The caller needs to make sure certain things are true, and then that's a precondition, and then the code itself will guarantee that certain things hold after we return. That's a post condition, okay? So, for instance, function match. Check if the array needle, a little small array, small string, occurs inside the middle of a big string, which we'll call hey. So look for needle inside hey. So needle and hey are both of type string. We have a location, which is a positive. It does needle and hey at the position lock. Okay, and here's the code. This is actually the code right here. Return Boolean is, and this is a for all loop. It's like a for loop, but it keeps looping through, making sure a condition is true. This condition after here. For all means, hey, do this for loop, make sure the body is true, and if it's ever false, return false. If they're all true, return true. Okay. Lisp programmers would call this AND map. For all I in 1 up to the length of needle, the small string we're looking for. Okay, so for each character of that small one, check that needle sub I, the ith character of needle, is at hey, loc plus I minus 1. Okay? That's the actual code for is this small string inside this big string at a certain location. With, and here's a precondition, that hey, that loc that you're looking for had better be a number that is in this, between 0 and this thing here. Hey length minus needle length minus 1. Okay? If loc is bigger than that, yeah, if loc is negative, we already have loc type being positive here. So that's a precondition already. A type is a precondition. Hey, the caller must make sure that loc is positive. And if it's not, it's going to signal an error. Perhaps at runtime, perhaps at compile time. Okay, but now there's an additional precondition. Loc has to be in this range here. And by putting it as code, first of all, the person calling it is reminded, oh wait, when I call this, I better make sure loc is such and such. Otherwise, this code would signal a index out of bounds. Okay. But if I violate somebody else's precondition, it's okay if they do something wrong because it's my fault. I gave them a bad input. So, okay, so that's an example of a function with a body and then, or functions and a body. We're also demonstrating this for all loop. And then how you attach a precondition to a function. Okay. And I'll go through it. What's an example of a postcondition? Hey, search for just the small string anywhere inside the big string. And once we have this match function, it's going to be pretty easy. Just call match at each location. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So there's actually a precondition that the thing you're looking for, the needle, had better not be bigger than hey. So needle length has to be in this thing here. And again, this is a type, 1 dot dot hey length. So I have to have a value of that type. Okay. Here's the postcondition, kind of long there. And this postcondition ends up being like the code you would have almost. But okay. But the nice thing is if you list this postcondition, other code can look at your program and verify certain things about it. If you're writing code that's going to be controlling an F-18 fighter, it's good for the compiler to be able to look at things and prove that certain things won't go wrong. That's really important. Rather than just saying, hey, we have some good programmers and they even wrote a bunch of unit tests and they don't think anything's going to go wrong. That's different. Putting down this postcondition, and you can, if you want to, try to go look through that. Let's look at this first part. Search result is in 0 to hey length minus needle length plus 1. Okay. We're returning where it, either 0 if it didn't return, it turns out, or the index where needle starts in hey, and that index has to be, can't be right at the end of hey length. It has to be a little backed off by a little bit. So, okay. So it's either 0 or it's in 1 to hey minus needle length plus 1. And then there's also this condition, this is part of the post condition. If the search result was bigger than 0, if it was there, then match occurs at that point. Okay. If search result was 0, then here's our post condition. It doesn't occur in there. It really doesn't occur. And I'm saying that as a post condition. You can rely on this. Okay. How do I say it doesn't occur? I'd have this for all locations, not match. Okay. Whew. So, wow, this is a really pretty cool type system, I have to say. It's letting you do a lot, and it's letting you do a lot that helps programmers, also helps compilers prove things and verify things. So, okay. So, and again, Spark is the name of this proof assistant that is sort of built in, runs alongside the Ada compiler. You have to ask for it to be run. It's not done automatically. It's a separate tool. So, okay. And now we'll just end up, well, whew, we can take off our thinking caps. Just a few small things I'll mention really quick. Ada is not an acronym. It does not stand for anything like the American Dental Association. Ada is named after Ada Lovelace, Ada Countess of Lovelace. Ada Byron King is the daughter of Lord Byron, so the poet. And she worked with Charles Babbage. He was developing the idea for the hardware for the machine, and she was actually writing programs that would run on that machine. So, okay, the analytical engine and all that stuff from your ITEC 100 class. Okay, Ada. The U.S. military is one big place that uses Ada. They want high reliability software. It's really, really, really super important in people's lives around the line. So, okay. Yeah, and at the time it was introduced, people were saying, hey, this is, like, it included generics, and they said, that's too tough. You can't solve that problem. Java came in with no generics and finally added them in 2005, okay? The idea that you can write numbers and use an underscore when you're writing a numeric literal in the middle of your program, you may have noticed that earlier. Yeah, the underscores, you can take them out, you can leave them in, you can put them wherever you like. You don't have to do them every 3, but it really helps readability. It's a pretty simple idea. No hidden gotchas with that one. Java, you can now do that. They said, that's a pretty good idea. Okay, we'll put that in there. So you can actually do this with your Java numbers as well. Okay, so, okay. I'm not going to talk about, you can go and follow these links about some particularly notable software failures. So, okay. And in general with this class, it's a fun class. We'll be writing programs. Go ahead and start on working on installing Ada on your own machine if you would like, you can always log on to the Rux compute server and use Ada from the command line there, or nat make. I'll have a reference to some pages on how to install this on your personal machine. So, okay, and do start programs early, because you know the hardest program in any language is Hello World. Just getting things to compile, getting your environment set up, and then when you're writing programs in Ada, because you're learning a whole new syntax, you're going to have a lot more stupid errors of, you know, it's not compiling because there's no word with that you want there, and the error message may or may not be very helpful, and you know, hopefully it's helpful, but it's not always. So yeah, start your programs early, particularly in this class. And I will talk with you in the next class. Thanks.